Know about capacitor circuits, let's take a look at resistor circuits. And to get us started, let's define what we call electric current. We define current as which we designate by I as being the infinitesimal amount of charge that passes a point in an infinitesimal amount of time. That would be instantaneous current. So to think about that, if I had a wire here, I would focus in on one point and I'd watch the charge go by and count how much charge went by that one point per time. And that would be what I define as current. This charge flow is assumed to be positive, and so we have positive charges moving predictably from the positive terminal of the battery to the negative terminal of the battery. And so if we imagine positive charges flowing to the right, that actually would be the same mathematically for us as negative charges moving to the left. In other words, two wrongs make a right in this sense. If we are wrong about the charges, but we reverse the direction, the results will be the same. And in fact, we're assuming positive charges moving from the positive terminal to the negative terminal in one direction, but the reality is we actually have electrons moving from the negative terminal of the battery to the positive terminal of the battery. So we do have the two wrongs being equal to a right. As far as we're concerned, it's not going to change our analysis to assume positive charges in positive direction. The only time it would bother us is if we were doing an investigation into the Hall effect, which actually helps us determine what the charge carriers are. But we're not going to worry about that right now. So we're just doing circuit analysis. We're going to assume positive charges moving in a positive direction. The System International Unit for current is the ampere, which is a coulomb per second. So consider this wire. We've got this wire, and we're going to consider a section of this wire. And the length we're going to look at is some length delta x, which is equal to the velocity of our carriers, drift velocity, v sub d, times some interval of time delta t. So we have this length, and we have this cross-sectional area. We have a volume equal to that length times the area for that cylinder. Enclosed within that volume are some charges. We're going to say those charges move some distance equal to delta x, their velocity times time. So if n is the number of charge carriers per unit volume for this material, then the total charge that is in this volume, in this segment, will be equal to the number of charge carriers per volume for this particular material, it could be copper, gold, silver, whatever, times the volume, so that will give us the number of carriers, times the charge per carrier. If it's an electron, the magnitude of that charge will be 1.6 times 10 to the minus 19 coulombs. So this will be equal to n times the cross-sectional area, the drift velocity, delta t, times q. Bear with me, we're headed somewhere with this. So our average current will be equal to this change in charge per time. From our previous equation, the delta t's will cancel out, and we have that our current is equal to the number of carriers per volume for this material, that's an intrinsic property, times the charge per carrier, cross-sectional area, times the drift velocity of these carriers. What do we really mean by this drift velocity, this drift speed? Well, these carriers are going through, they're electrons in reality, and they are trying to make their way through the wire, and there is some impetus for them to move forward, and that is the voltage that we've applied, which is actually applying an electric field through this wire. So that impetus is causing these electrons to move. But it's not necessarily easy, because there are other electrons there as well, and they're repulsed by them, and then there are positive atoms, and they're attracted to them. So as they're moving along, they're just being kind of pushed around like this, and so their actual path may be somewhat disjointed, but they're still trying to make their way forward because there's an impetus for them to do so. So they are making their way through, and the one question you might have is, really, how fast are they actually going? How fast are they making their way through in this wire? I'm glad you asked that question, because we're going to solve that next. Consider this. Calculate the average drift speed of electrons traveling through a copper wire with a cross-section area of 1 square millimeter when carrying a current of 1 amp. It is known that about 1 electron per atom of copper contributes to the current. The atomic weight of copper is 63.54 grams per mole, and its density is 8.92 grams per cubic centimeter. So, we have a wire, 1 square millimeter of thickness is actually pretty thick wire, carrying a good current. 1 amp is a lot of current. So we got a wire carrying a good current. We want to find out how fast are the electrons traveling through this wire. Well, let's calculate our little n value for copper. We know that the volume of 1 mole of copper is equal to 0.0635 kilograms per density, which is 8.92 times 10 to the 3 kilograms per cubic meter. That's going to give us a volume of 1 mole of copper atoms of 7.095 times 10 to the minus 6 cubic meters. That should contain 1 mole of atoms, which will also be 1 mole of charge carriers, because there's 1 carrier per atom. So we're going to have Avogadro's number, 6.02 times 1023 per volume of mole, and that will give us 8.48 times 10 to the 28 electrons per cubic meter of copper. Right, so that is our n value. That's our number of electrons per volume. Taking our previous equation and solving for the drift velocity, our drift velocity should equal the current over this n value for copper times the charge per carrier divided by, or the whole thing divided by the area, cross-sectional area of the wire. We have 1 amp, 8.48 times 10 to the 20 electrons per cubic meter, 1.6 times 10 to the minus 19 coulombs per electron, and the cross-sectional area of the wire is 2 centimeters by 3 centimeters, or I'm sorry, 1 square millimeter, so that's 1 times 10 to the minus 6 square meters. This gives us a drift velocity of 7.39 times 10 to the minus 5 meters per second. Really? That's how fast the electrons are moving through a good wire carrying a very good current, a good wire carrying a good current, and they're only moving at 7.39 times 10 to the minus 5 meters per second. That's pretty slow. I mean, I was always told when I was learning this stuff that electricity traveled at the speed of light. And this is much slower than the speed of light. In fact, let's see, there's 3,600 seconds in an hour. So this is about 0.26 meters per hour. So what we're saying is that these electrons are traveling 26 centimeters or 0.26 meters that far in 1 hour. So it would take them 4 hours to traverse 1 meter. Really? I mean, when you turn on the light's there. I mean, you hit the switch, it's there. How could those electrons be taking 4 hours to move every meter? I mean, it's almost instantaneous when you turn on the lights, is it not? The answer to this quiz is yes and no. We have electrons, and they are traveling indeed at this speed. So this wire of 1 amp, the electrons are actually taking 4 hours to travel 1 meter. The thing is, though, when we're talking about current, we're talking about charge passing a point per time. So all I need to do is have current, is to have charge past that point. The charge is already in there, though. Charge is all the way through the wire. Every copper has a charge associated with it. So there's charge all the way through the wire. All I need to do is push that charge past that point, and I've got current. It's kind of like when you've had your garden hose out all winter and you're ready to wash your car for the first time in the spring, and you turn on the spigot for the first time, and the water has to go all the way through the hose before it finally comes out the other end so that you can use it to wash the car. That takes time, and that's like the electrons moving through the wire. But if you wash your car the next day, there's already water through the hose, so as soon as you turn on the spigot, water's coming out the other end. And so immediately when you turn on the spigot, you've got water there at the end of your hose. That's kind of like the way the wire is. All you need to do to have current is to have the charge that's already there start moving. And if it starts moving past a point, you've got current, charge per time, moving past that point. That's how AC current works. AC current is alternating current. It goes one way and then the other way. In order to have current, all you need to do is make that charge move this way and then this way. It never actually goes through the full circuit. It's actually just moving back and forth between that point there. So the electricity is basically near the speed of light, because the action of moving that charge past a point right there is almost instantaneous, but the actual movement of the charge carriers is pretty slow, 4 hours for 1 meter. How about that? So you won't see this diagram in your book, but it kind of illustrates that point, that the electron flow is kind of like the mechanical flow of water through a pipe. The current density in a wire is defined as the current per cross-sectional area of the wire. Taking our current from what we just defined, NQ, area, drift velocity, divided by the area, we have that the current density is the number of carriers per volume for that material times the charge per carrier times its drift velocity. Turns out for many materials it is true that the current density, which we designated by J, is equal to another constant which we call the conductivity, designated by sigma here, times the electric field. So the current density equals the conductivity times the electric field. This statement is the electrodynamics statement for Ohm's law. And if you take a course in electrodynamics after this one, you probably will see this kind of statement used a lot in that course. We are not going to use Ohm's law in this form. We're going to transform it. We'll note that the resistivity is 1 over the conductivity. So we define rho as the resistivity as 1 over the conductivity, still an intrinsic property of whatever material we're using for our conductor. So now we have, since the current density equals the conductivity times the E field, if we replace for the current density current per area, I per area, and we replace for the conductivity sigma 1 over the resistivity rho, and we replace for the E field the voltage divided by the length of the wire. For a constant E field that would be true. Then with a little bit of algebraic rearranging, we have that the voltage is equal to the current times this expression, resistivity rho, length of the wire over the cross-sectional area of the wire. Or we can write it like this: the voltage is equal to the current times the resistance. That is the Ohm's law that we're going to use for our circuits, where the resistance is equal to the resistivity of the material that we have for our wire times the length of the wire divided by the cross-sectional area of the wire. Now the resistivity is intrinsic to the conductor. It's going to be slightly different for copper, gold, silver, aluminum, that sort of thing. The length, we can understand that the resistance should be greater if we have a longer wire, because if we were an electron trying to get through that wire, the longer we go, the more resistance we're going to have in the long run. And it should be inversely proportional to the cross-sectional area, because imagine this. Say you're driving down a highway and you only have 2 lanes and there's a lot of traffic. It's going to be hard to get around. If you want to try to go faster, you really can't, because there's just too many cars and you can't really get through with just 2 lanes. But if you're in that highway and now you have 6 lanes with the same traffic, then all of a sudden you've got more options. And you can go out to these outer lanes and go by and then come back in. So you can get around all that traffic. You have less resistance if you have more options. So if you have more cross-sectional area in your electron, you got more options. You have more opportunity to go further, and hence the resistance that you encounter will be less. Note that V equals IR. If we were to graph it, voltage as a function of current, we'd have a straight line. It's a linear relationship, and the slope of that line would be the resistance. Let's try this resistance formula out. Calculate the resistance of an aluminum cylinder that is 10 centimeters long, has a cross-sectional area of 2 times 10 to the minus 4 square meters. Repeat the calculation for a glass cylinder of resistivity 3 times 10 to the 8. So for aluminum, the resistance would be the resistivity of aluminum times the length of the cross-sectional area. I guess we have to look up the resistivity of aluminum, which is 2.82 times 10 to the minus 8 ohm meters. Multiply that by the length. 10 centimeters is 0.1 meters, and the cross-sectional area was 2 times 10 to the minus 4 square meters, giving us a resistance of 1.41 times 10 to the minus 5 ohms. And that's our symbol for resistance, the omega ohms. For the resistance of the glass of the same dimensions, that would be the resistivity of glass, 3 times 10 to the 8. Same length, same cross-sectional area. The resistance is 1.5 times 10 to the 13 ohms. So there are 18 orders of magnitude difference between these two devices, these two resistances. In other words, aluminum is 18 orders of magnitude more conductive than glass. Kind of makes sense because glass is amorphous. It doesn't have a regular lattice structure to its solid, and doesn't really contribute free electrons the way that conductors do. So it's a very good insulator. So the aluminum is 18 orders of magnitude better conductor. That's 10 times 10 times 10 times 10 times 10 times 10 to 10 times 10 times 10 times 10, 18 times. That's how good the aluminum is as a conductor as opposed to glass. For most metals, the resistivity, which is an intrinsic property, has a temperature dependence. The resistivity is equal to some reference resistivity, usually at room temperature, times 1 plus another constant, alpha, times delta T, and this alpha is called the temperature coefficient of resistivity. So rho is the resistivity at temperature T, rho naught is the resistivity at some reference temperature, usually room temperature or possibly 0 degrees Celsius. And delta T is a change in temperature. It follows the same for resistance. Resistance is equal to some reference resistance, 1 plus the alpha, which is the temperature coefficient of resistivity, another intrinsic property of whatever material we're using, times a change in temperature. So if the temperature were to go up, the resistance would go up. And if the temperature were to go down, so that delta T was a negative value, the resistance would go down. Why is this so? Say I had a wire, and you are an electron trying to get through the wire, and you're going through, and you're encountering problems. There's other electrons who are resisting you, and there's positive ions that are attracting you, and you're being pulled all over the place. If the temperature goes up, all these other guys are moving more. And the atoms are moving more, they're moving around more because of the temperature, and so are the other electrons. They're moving and shaking around more like that. So if you're trying to get through, it's going to be harder when these other components are moving around more because of the temperature. Hence, you're going to encounter more resistance. On the other hand, if the temperature goes down and got really cold, maybe approaching absolute zero, and all these other components, they're not really shivering, but they're actually just frozen there, you can actually find a path through much more easily. So the resistance goes down as the temperature goes down. In fact, as you approach absolute zero, many of these materials, these metals, will go superconducting, which means they will conduct electricity without any resistance at all. That's a special case where they pair up in Cooper pairs and they make it through. That's at very, very cold temperatures for these metals approaching absolute zero. There are a branch of substances, ceramics, that have high temperature superconductivity as well. That's on the order of the temperature of liquid nitrogen, which is relatively high compared to absolute zero. I only mention all that because that's the nature of my study for many years. My graduate thesis and my work at NASA was to deal with high temperature superconductors. Of course, NASA would be interested in that in space, because if you're in the shade in space, it gets pretty cold there, and you can use these things without any problem. So I just had to put that plug in there. Let's try this resistance relationship in a problem. If a copper wire has a resistance of 18 ohms at 20 degrees Celsius, what resistance does it have at 60 degrees Celsius? So your change in temperature will be 60 minus 20, or 40 degrees. The temperature coefficient of copper is 3.9 times 10 minus 3 per degree Celsius. So our new resistance will be our old resistance at 20 degrees, 18, times 1 plus this temperature coefficient, 3.9 times 10 minus 3, times 40 degrees, 20.8 ohms. So we actually go up maybe about 15%. This could be a problem if you actually had circuits with designed elements and resistances designed to be fine-tuned to do something, like in a computer, and if the temperature were to go up dramatically, then all your components are going to start changing the way they work, and it could affect the performance of your device. So a lot of times, if you saw computers and you needed them to do accurate measurements over a long time, you would keep them in a climate-controlled room, maybe keep the temperature constant so that everything they did would be on a consistent nature, and you wouldn't have to worry about temperature fluctuations changing your output. Electrical energy and power. We know from power, from Physics 1, is the rate of change of energy. It's how much energy per time we have. So in turn, we could say that energy would be equal to power times time. And since for a charge, our energy is equal to the charge times the voltage, we got that from chapter 25, we could say our power is equal to our change in energy per time, which would be the change in charge times voltage per time. But if we had the change in charge per time, that is indeed current. So this would be equal to the current times the voltage. In an electrical DC circuit, the power is equal to the current times the voltage. P equals IV. Sometimes called Ohm's law for power. If we had this in a device like a resistor, then the power would equal the current times the voltage of that resistor. The voltage of a resistor obeys Ohm's law, V equals IR, so the power dissipated in a resistor is going to be I squared times R. This is sometimes called resistive heating. We could also write this as power dissipated in resistor as voltage squared divided by R. These are very useful formulas, and we're going to use it a lot when we start doing circuit analysis with resistors in the next chapter, chapter 28. So these are formulas we're going to take with us into the next chapter. That concludes our introduction to resistor circuits, chapter 27. Let's go on into true circuit